Hi, good morning. Thank you very much. I really appreciate the opportunity and invitation to share with you all NASA's current status with regard to the asteroid redirect mission. Do I have something here? I apologize. I should have asked before. Thank you. Thanks. There we go. All right, so y'all may be familiar with NASA's strategy for leading to the ultimate horizon destination of Mars exploration, including what we call Earth-dependent activities, which are being implemented on the International Space Station to both inform and prepare for deep space journeys, including Mars, as well as activities in the proving ground of cislunar space. And the asteroid redirect mission is one of the key activities in the proving ground, so I'll speak to you about that today. I'm not going to get this right. Okay, here we go. This is a brief articulation of what we see as all of the contributions that can be gained from the hardware and operations on this mission towards future exploration, including the demonstration of advanced high-power long-life solar electric propulsion capability, including the high-efficiency large solar arrays, the in-space EVA capability development that will be demonstrated on this mission, as well as implementation of common hardware such as the International Docking System and common rendezvous sensors. Key aspects of the asteroid redirect mission that we strongly believe will contribute to future deep space human exploration are the beginning of moving large objects through interplanetary space-like trajectories using high-power solar electric propulsion, the initiation of integrated Orion and robotic vehicle stack operations in deep space orbits, like we'll do in the lunar distant retrograde orbit, the implementation of lean development for robotic capabilities, which complements the core human spaceflight crewed vehicle developments currently ongoing within NASA, and the opportunity for our workforce and the broader workforce to learn and share together across science and human exploration in a large-scale partnership effort. The redirect mission has 3 segments. As you know, the first is identifying candidate target asteroids. And this segment is being led by the Science Mission Directorate and specifically Lindley Johnson's Near-Earth Observation Program. The redirect segment, for which the planned demonstration of advanced high-power solar electric propulsion in the Space Technology Mission Directorate will be leveraged. We currently have 2 options we're looking at. Option A is the capture and redirection of a single small free-floating or free-range asteroid. And option B is the acquisition of a large boulder from a larger asteroid. And then the third segment is the exploration and gathering of samples from this asteroidal mass, which will be available in cislunar space, specifically a lunar distant retrograde orbit in the mid-2020s. We see ARM as implementing as an opportunity to leverage ongoing capability developments already happening within the agency to implement an affordable and compelling mission in the mid-2020s in cislunar space. Both the systems and operational aspects of the mission will significantly contribute to future long-duration deep space missions such as to Mars. And the technologies, systems, and capabilities are viewed as a core part of the sustainable Mars human exploration strategy, including, again, the high-power SEP systems, the advanced in-space EVA capabilities and upgrades of the life support system, the implementation of common standards and systems which would feed forward to extensibility, as well as a request that we sought in a recent broad area announcement for potentially modifying commercially available spacecraft buses to implement this mission, with ideas for future upgrade capability. So further leveraging that idea of lean robotic development complementing our core human space-flight crewed vehicle capability. Over the last year, our internal studies have determined that essentially the same flight system can accomplish both options A and B for capture. And regardless of the capture options, there would be substantial asteroid mass attached to this high-power SEP vehicle in a lunar distant retrograde orbit in the mid-2020s. The current objectives of the mission have evolved based on our internal studies over the last year, and y'all may have seen this. Originally, we had kind of two tiers, one with primary objectives and the second under benefits. And we've moved a basic planetary defense demonstration technique demo up into the main objectives, and also found that we can provide opportunities for science and in situ resource utilization, for example, and partnership opportunities in the mission. So those are also currently listed within the 5 core objectives. NASA's NEO program assets are being brought to bear and leveraged to identify and characterize candidate targets for this mission as well. The upgrades that are being implemented and enhancements in the NEO program beginning FY14 and out are a key part of all of the progress that we've made this year, and we're very grateful to that very competent team. In addition, the characterization assets, including radar enhancements, are ongoing. Improved operability and maintainability of the IRGF, and clearly this mission has taken advantage of the use of Spitzer for asteroid observations over the last year. Internally, we've completed 3 studies over the last year. One was looking in detail at the original, what we called the reference concept of enveloping and maneuvering a single small asteroid to the cislunar stable orbit. We also did a good amount of work led by Dan Masnick at the Langley Research Center looking at this option B and acquiring a substantial coherent mass from a larger asteroid, which we all call a boulder. We have leveled those two based on our internal studies, both technical and programmatic, to an option A and B, which are currently being considered for down select and towards MCR. The Johnson Space Center has also done quite a bit of work on looking at feasibility, both technical and programmatic, of the crewed mission in the mid-2020s, and we'll share some of those recent results with you today. We also chartered and had chaired by one of our most senior systems engineers, an impartial gentleman from Marshall Space Flight Center, a robotic concept integration team, which did an assessment and presented to senior leadership in February, and have included input from the SBAG and the CAPTEM in that, and we have ongoing engagements with those folks as well. So here are just some simple graphics of the option A and B. There's risk reduction work, including subscale test beds, currently being developed within JPL and Goddard Space Flight Center in Langley. In addition, we have the broad area announcement, concept development and risk reduction that we requested that were actually being awarded by the 25th of this month, announced in June. And the down select decision is planned for mid-December. This is a graphic of the reference internal flight system that we determined could implement either option A or B. Basically, this system takes advantage of lean, simple interfaces, lean development, the solar arrays that went through the phase 1 technology development activity in the Space Technology Mission Directorate, just having wrapped up last month. The reference concept includes a capability for 10 tons of xenon, but you'll see that we actually don't need that for most of the mission concepts. So then the question is, how would we make use of this remaining capability in the distant retrograde orbit after this mission? and we're working with the SBAG and others on investigating that question. Next slide. Our understanding of current candidate target asteroids has also evolved based on the work that has been done in the NEO program and the observations over the last year. We currently have 3 valid candidates for option A and continue to observe and both identify and characterize other candidate options, and will continue to do so. For option B, there's lots of potential candidates. We currently have 3 valid candidates for option B as well, including Itokawa, Bennu, and 2008 EV5, and then expect the Hayabusa target to be added to that list as well. Just our articulation here that when we talk about return mass from a system architecture and mission design perspective, that actually means different sizes and compositions are possible. And we use this slide here in sharing with our broader community the implications of various asteroid compositions as well as orbits and what we can return in terms of return mass. The option B, which are shown here, has less possible return mass due to the larger distance that those targets currently have from Earth and lunar return. There's 3 planetary defense technique demonstrations on the table across option A and B, including the ion beam demonstration, gravity tractor, and enhanced gravity tractor options. Next slide. We're happy to share with you any of those details if you'd like as well. And then a little bit of status on where we are with the crewed mission concept planning, again using Orion and the Space Launch System vehicles to launch our crews to the lunar distant retrograde orbit in the mid-2020s, execute these complex multi-hour extravehicular in-space expeditions to retrieve samples and return those samples with the crew in the Orion crew capsule. The mission is envisioned to be 26 to 28 days with 9-day outbound, 9 to 11-day outbound, 5 days actually in the lunar distant retrograde orbit, implementing those 2 multi-hour, potentially 4-hour EVAs, as well as other opportunities, and then the return, totaling 26 to 28-day missions. We're also implementing common sensors that have undergone quite a bit of evolution and original use on shuttle and station. And a mission kit concept that, in addition to use of heritage hardware, allows us to reduce the cost of the crewed mission. So there's several kits that would be added in addition to the core Orion capability, including enhancing spacesuits, the repressurization of Orion, EVA comm, and all of the equipment needed for sample return. Our folks at JSC have looked in detail over the last year at the actual feasibility of using this MESA suit to accomplish this mission. From initial ingress and demonstration of the testing capability of the suit to actually testing modifications of the suit for enhanced mobility, including shoulder mechanisms, enhanced gloves, portable foot restraint techniques, culminating in 2 mission sims of the 4-hour EVA missions, including egress from Orion, translation over the SEP spacecraft, sampling, very rudimentary sampling technique, feasibility demonstration, and then translation back over the SEP spacecraft and ingress into Orion. And basically our knowledge at this point is that it looks like the use of these suits could be feasible for these tasks and for completing this mission. Thank you. Our BAA has resulted in the selection of 18 proposals totaling $4.9 million, looking at a variety of concepts that will be wrapped into our down select review and mission concept review, including for capture systems, as well as the potential application of modified commercially available SEP buses to accomplish this mission. Inherent in that would be the ability to upgrade those buses for future long-duration exploration purposes, and partnerships for enhancing the crewed mission, such as ISRU, and the use of specific tools. We're also engaging the science community through the Small Bodies Advisory Group and the CAPTEM. We've had several external forums and requested feedback and are continuing that in current and future opportunities. We also have in the BAA's partnership for both the robotic spacecraft and the crewed spacecraft that are undergoing concept development. We look forward to continuing that communication and invite your feedback as well, including in the GER session tomorrow. The CAPTEM has provided an analysis and assessment of several aspects that are important from a sample curation and planning perspective, including the application of a ground-based science team. We're actually thinking of an investigation team that would include science, and several aspects of the hardware used for sampling as well as containment. Just a note that the NEO program has an annual solicitation. You may be aware of that. We're happy to include input through that mechanism as well. And then our near-term planning schedule leading to mission concept review planned for this February, including BAA input, down select between option A and B, the solar electric propulsion technology development and demonstration, our risk reduction activities, and the crewed EVA demonstration. So this is a brief summary. I'm very happy to be here and look forward to understanding better your perspectives and feedback, and happy to take any questions.
Yeah, thanks so much. I neglected to mention, by the way, that Michelle was an invited speaker, so thanks for taking us up on that. Jack, you were first since you didn't get to ask yours last time. Go ahead.
Thank you, Greg. Jack Burns, University of Colorado. The recent NRC study on human spaceflight did a comparison of technologies in moving forward to Mars, looking at going to the surface of the moon versus asteroids. And their conclusion seemed to be that quite a number of the technologies for ARM would not be useful in moving forward to Mars. They would be thrown away, if you will. I think is the phraseology that they would use. And a small number relative to what they looked at for the moon. I haven't seen a lot of reaction from NASA on that particular aspect of that report. Can you comment on that?
Sure. So the chapter 4, I think it was, where that analysis was presented in the NRC report was, my understanding, developed in 2013 when we had initially rolled out some of the initial concepts for implementing this mission. We didn't actually brief them on our work or our concepts, so we believe there were a number of assumptions made in the programmatic analysis as well as the assumptions about the SEP technologies. I think their point about the capture and control of non-cooperative objects is a very good point, and so we have actually, before the report came out, matured our understanding of the feed forward and contribution to Mars missions, as well as what exactly we'd be using for the capture piece.
Great, thanks. Are there any other questions? Yeah.
Hi, Brent Barbie and NASA Goddard. For the planetary defense demonstration concepts that you mentioned, I'm wondering if you all have considered including kinetic impactor. If not, I would strongly encourage you to do so because of its practicality and its ability to respond to short warning time scenarios.
Yes, thank you so much. Our thought on kinetic impactor would be that it could be potentially secondary payload, but isn't really a part of the main mission the SEP and capture payload.
Okay. We can take one more. Bill?
So I was curious about, I have a bunch of questions, but I was curious about the EVAs. So my understanding from a previous meeting is that we're going to have 2 4-hour EVAs to do everything with the astronauts, and that's really all we can really do. How much time will that give us with the extracting the sample and getting back? Because a lot of that's going to be setting up the equipment just to get to the asteroid. So what's the current timing of interacting with the asteroid in the present analysis?
Yes, thanks. So the 2 4-hour EVAs is kind of an initial concept that's currently being envisioned. We would continue to look at what would really be possible with repress kits, et cetera. I haven't seen a detailed timeline other than the MESIS testing that we've done, and honestly would have to get back to you in terms of how much time we currently envision as being possible for interaction with the material within that time.
Jim, if you have a very quick one, we can take it.
Just a quick follow-up. So on Apollo on surface operations during a 7-hour EVA, the time spent on details of the science was less than 15 to 20%, just for frame of reference.
Thank you.
Thanks. Thanks again, Michele.